In its initial version, this Laboratory 7 project already implements the light calculation in both vertex and fragment shaders. But I would like to try this experiment shown in our presentation with just diffuse light part and use only the vertex shader to do the computation, which should make it fastest way that you can compute the light. But remember, this is impossible for the specular light because it must be computed for every pixel. So unfortunately we'll lose the specular appearance in this experiment, but let's give it a try and see how it looks like. So first we're going to make a change here in the vertex shader, and we simply replace the portion of the original code with the new one. So we're going to take the new code from this example and replace this part with the sample code like this. And we also need to add this output of interpolated color. I'm just going to place it right here above the main function in the vertex shader code. And to keep the changes at a minimal, we have to make some variable adjustments. For example, we have to replace this s underscore vnormal with vnormal because that's the name of our vector here. So I'm just going to replace this with our name vnormal. This came from the sample. Then also we need to change m rotations to just mr because that's what we have in our shader. And also we name it light position, but in the sample it's called vlight. Okay, so we're going to make this change as well. So this changed, this changed, this changed, and this as well. And now for the fragment shader, which is also shown right here, just need to make sure that we accept this interpolated color already calculated here in the vertex shader. So we're going to add this new input variable in the fragment program. So again, I'm just going to add it right above the main, and then replace all of this set of formulas with this single statement that uses the interpolated color for every fragment. Okay, like this. So I'm just going to save all my changes, and I'll show you both side by side. Okay, so this is what I have so far in my code. And since this is only the changes applied in our shader programs, I don't have to rebuild the executable file, so I'm just going to press Ctrl F5 to run it again. And you can see that this time, so I'm just going to press Ctrl F5 to run the program. As expected, the specular light is gone, and since we only use the light color in this quick copy and paste example, it appears that the light color we use is plain yellow, because we just have it hard-coded directly in the vertex shader code. Right here we have the light color hard-coded to just red and green, which gives us the yellow shade. Alright, so what about the geometry? Where is the light position relative to the object? We actually have this here in our main file, and this is a good time to examine the setup of the light object properties. So this is our main function, and this is where I configure the light position, the ambient, diffuse, and specular light components that we currently not using in our update of the shader code. But this is the light position, and because all of this computation is happening inside vertex shader, let's move it to the next document group side by side with this. And as we want to talk about the geometry, we need to understand where the object is positioned relative to the light location. And because we only compute diffuse light component in this vertex shader computation, we need to take another look at diffuse lighting and understand how we obtain this angle of incidence of light. So first, what we do here is that we rotate our normal vectors. As the object rotates in space, its normal vectors also have to be rotated. So let's locate creation of this rotation matrix, and this is happening in the rendering function. As usual, what we do is that we compute the scaling matrix, then we apply rotations, and then translations. And of course, in this case, translation is combined with scaling, and the rotations are computed separately. And our rotation is pretty simple. We just take the y-axis and we specify the theta rotation degree, and we set it up as our rotation matrix. But here, to make a demonstration of more universal approach, what is possible is that if we take the scaling, then apply the rotations, then apply the transformations, we have our final version of the modeling matrix that transforms our model into the world coordinates. And there, if we already finish with this modeling matrix from linear algebra, we know that it tells us that if we have any sort of 3D transformation matrix, we could extract out of it just pure rotation transformations by taking inverted matrix and then taking the transpose of that. Just very briefly, this is what matrix inverse means. I just googled this image and found it on Math Bootcamp's website. So the inverse matrix is such matrix that when you take the original and multiply it by its inverse, the result of multiplication is the identity matrix. And the notation for inverse matrix is either A prime or A superscript -1. And the transpose matrix in linear algebra is a matrix which is flipped over its diagonal, which means that it switches its rows and columns like this, right? So the original row ABC becomes the new column ABC, and so forth. Okay, so the combination of these two operations gives us the magic matrix with all pure rotations, which we apply to our normal vectors right here in our vertex shader. So this is a very nice trick that we have the modeling matrix complete, and now using this math we extract pure rotations. So right now the normal vectors are all taken care of, and I'm also noticing, because it says normal in camera space, if we want to do this computation in camera space, we also have to multiply by the view matrix. So here we can add this as well, just to be consistent with the naming of this variable. So now at this point, our normal vectors, right? So if this is our object and we have our normal vectors sticking out like this, right, in all directions. So all of these normal vectors are already rotated and already are in camera space. So let's just say that this is our camera space arbitrarily, right? So this is the system of coordinates which is attached to the camera. And of course we're looking in the negative z direction, and the camera is positioned right at the origin of its own system of coordinates. And our object happens to be behind the XY plane, so it becomes visible. And then if our source of light is located 10 units behind the camera, then this is our direction of light. So this is our second vector that we need for this type of computation. So this computation happens to be in the camera space, and because we don't make any updates at all to the light position, the meaning of this is the light which is basically attached to the camera. Therefore, it is like the car headlights, in a fixed position relative to the position of the viewer, like a person driving a car and looking at the objects lit by the headlights behind the windshield. But in our case, the camera is stationary and instead the object rotates in front of it. So the last thing we can try is moving the light source a little bit. Okay, so this is our light position. So we can try moving it a little bit to the side, like perhaps we could try 15 units on the x-axis, in addition to 10 units behind the camera. Alright, so I'm just going to rebuild this code and try running it again. So you can clearly see that the light is now positioned on the right side of our object, and clearly the left side of the car is in the darkness compared to the right hand side.